Okay, I guess I'll get started. My name is Daniel, and today I'd like to talk about types, TypeScript, and the JIT. Oops. Got my hand. So first, a little about me. I'm part of the SpiderMonkey team at Mozilla. I'm also a delegate to TC39, the committee that's responsible for the JavaScript language standard. Y también soy ratón de biblioteca y estudiante perpetuo de castellano. Oh, thank you. And you may be wondering, what exactly is a spider monkey? Well, it's a member of the genus Ateles. It's considered the most intelligent New World monkey, and a little much in the way of thumbs to make up for their long limbs and tails. But what then is spider monkey? It's a JavaScript engine that's used in Firefox. The engine is a part of the browser that's responsible for running JavaScript code. And it consists of parsers, interpreters, just-in-time JIT compilers, a garbage collector, and a library of built-in functions, some of which I'll talk about in a little bit more detail today. But first, I'd like to talk to you about types. So this is Bertrand Russell. At the beginning of the 20th century, he was involved in a program to axiomatize mathematics. That is to say, he wanted to show that all of mathematics was provable from logic. If he seems a little bit preoccupied, it's because he has a problem. And this is it. Today we call it Russell's paradox. And what it says in words is, consider the set of all sets that aren't included in themselves. Then they're only included in themselves if they're not included in themselves. And that's a serious problem for him because that's a contradiction, and anything at all is provable from a contradiction. But he had an idea, and his idea was to use types. So basically, if we have sets a different type from the other elements, then we'll stop people from doing silly things with them. And that's more or less what we use types for today. So what exactly is a type? Well, it's a set of values with a rule for determining membership, a set of allowed operations, and possibly, in computer science terms, an underlying machine representation. So let's look at an example. Good old JavaScript numbers. So we have a rule for determining membership. We take all valid IEEE 754 double precision numbers. That's an international standard for floating point arithmetic. Except in JavaScript, we have only one single not a number value instead of the over 9 quadrillion possible values that are allowed for in IEEE 754. And there's actually a reason for that, but I won't get into it today. We also have a set of allowed operations, addition, subtraction, etc., and an underlying machine representation, which comes from that standard. If you look closely, you'll notice that there's a sign bit, which is why we have both positive and negative 0 in JavaScript. So I know we saw a little bit about this morning in the lovely talk about OCaml, but I wanted to talk a little bit about type checking and type inference as well. So type checking is determining whether or not programs are following the rules for their types properly. So we have dynamic typing. This is what JavaScript is doing. That's why we get good old type error exceptions when things go wrong. Or we can have static typing. This is what TypeScript does, which means types are being checked at compile time. And type inference is a related concept where we basically try to guess the type of a variable based upon how it's being used in the program. So two more important concepts are soundness and completeness. So a type system is sound if no program with type errors will ever type check successfully. And a type system is complete if every valid program can be type checked successfully. And Kurt Gödel showed in 1930 that any sufficiently complicated proof system is either unsound or incomplete. So we can have soundness or completeness, but not both. And that also happened to ruin Bertrand Russell's project, Axiomatize Mathematics. So I'd like to talk a little bit about TypeScript now. So everyone here knows more about TypeScript than I do. I'm actually a C++ programmer. But basically, designed to allow gradual addition of static typing to JavaScript, allows for type annotations, does static type checking where types are known, uses type inference where possible, and it compiles or transpiles down to JavaScript. So we saw earlier today as well that TypeScript's unsound. So I have a fairly simple example here. We have an array of numbers, and we have something that's going to access something off the end of that array. At runtime, that's going to be an undefined value. But as far as a type checker is concerned, this is fine. So is this actually a problem? Well, probably not. Like, the design goal of TypeScript is to allow the reuse of existing JavaScript code. So for the designers, it's much more important to be complete rather than sound, because people will be very annoyed if their perfectly good JavaScript code stops running. So after this morning's presentation, I'm sure everyone is thinking OCaml when they think of a language that's sound but incomplete. But my example is actually Rust's borrow checker. So it's sound but not complete. And what this means is if code passes the borrow checker, it's safe, at least as far as the properties that it checks are concerned. But occasionally, or more than occasionally if you're a beginner in Rust, perfectly fine programs are going to be rejected. And that's why part of learning Rust is kind of this painful process of training yourself to think like the borrow checker. And I should also point out that there's actually an open bug with the borrow checker at the moment, so it's neither sound nor complete. Okay, so I'm going to move on and talk a little bit about just-in-time compilation. So this is the process of compiling code at runtime instead of ahead of time. So why on earth would we ever want to do something like this? Well, we know empirically that most JavaScript code is only executed once or a handful of times. And we also know that compiling and optimizing code takes time, which means that there's a trade-off. And that trade-off is if the time to compile some code plus the execution time is greater than the interpreter time, then there's really no point in compiling code because the overall system is going to run slower. So I just talked a little bit about interpreters and talk about that a little bit more. So just backing up for a second, a bytecode is an instruction for a virtual machine. And a virtual machine is just an abstract definition of a computer. In the context of a JavaScript engine, it's something that we've defined to be closer to JavaScript than an actual CPU. And an interpreter is just a program. It's a program that implements this virtual machine that executes bytecodes and by extension executes JavaScript code. So talking about bytecodes a little bit more and bytecode generation. Here is an example of a relatively simple function. When the engine sees this function, what it's going to do is parse it. The parser generates what's called an abstract syntax tree. And once we have this tree, then we can walk through the nodes of this tree and generate bytecode that corresponds to the operations in these nodes. So here we have the bytecode that corresponds to this function. And once that's ready, it can be ingested by the interpreter and executed. So looking at that function in a bit more detail, talk about dynamic dispatch. And this is when we choose which code to execute based upon the type of the arguments. So we can call that with a number, and in which case we're going to have to branch the code to handle numbers. All kind of makes sense. But this being JavaScript, we can also perfectly reasonably call it with a string, which means we have to be able to branch the code to handle strings. This still being JavaScript, we can also call it with a Boolean, which means we have to be prepared to branch the code to handle Booleans. And if it sounds like this has the potential to be slow, it does. So what can we do to speed it up? Well, one answer is caching. We can store the results of these previous dynamic dispatches in what's called an inline cache. It's called inline because we're storing those results right next to the existing bytecodes. And what we do in SpiderMonkey is we use something that's called a stub, which is a chunk of native code that's been specialized for an operation and a type. So instead of having this generic multiply instruction that has to be prepared to handle any sort of type, we can replace it with one that's been specialized for a particular type. And this is actually a very effective optimization. It depends upon the workload, but we see something on the order of a 2x speed up over the C++ interpreter. So how else can we make this faster? What else can we do? Well, I'm talking about just-in-time compilation, so it's probably not surprising that's my other answer. And this means if we see the same source code often enough, we're going to compile it to native code. And we can actually make use of the type information that we've already gathered in the inline cache. This depends upon the engine, but in SpiderMonkey we have two levels of just-in-time compilers. We have what's called the baseline compiler, which compiles quickly, but it's only going to do a handful of optimizations. And we have Ion, which is our optimizing compiler. So it's slower, but it generates more heavily optimized code. And that's more or less just a trade-off between how much time we want to spend compiling code and how often we expect to be able to run it once it's done. So what happens when things go wrong? Well, in the context of this system, things going wrong is seeing an unexpected type. And we do what's called a bailout. In this case, we have to go back to our baseline interpreter. We can't use our inline cache. We can't use our JIT compiled code. This actually happens often enough, we'll end up throwing away our JIT compiled code, which is not great because we've already spent a bunch of time trying to compile it. So this is a situation we'd like to avoid if possible. And that brings me to the crux of my presentation, which is, does using TypeScript actually end up helping the JIT? And the answer is, it definitely doesn't hurt. Anything that's going to make that input more predictable in terms of type is going to help. So we'll see better use of inline caches, we'll be more likely to JIT compile code. But, as we've seen, TypeScript types don't always match engine types. So one example is TypeScript just has numbers, but inside the engine, inside SpiderMonkey, we have 32-bit integers and doubles. But we also saw this in the soundness example earlier. So TypeScript type checks something as a number, but we know it will actually end up being undefined at runtime. So what this means is, unfortunately, there's no guarantee that a TypeScript type will match what the engine sees. And that means the engine has to be prepared to do the exact same amount of work, regardless of whether or not TypeScript is being used or not. But I don't think that's really the end of the story. I mean, obviously TypeScript is a great tool. There's actually been academic studies that show that it improves developer productivity. And it's my opinion, like the mental model that comes from thinking in terms and types is really super helpful as a developer. So, pues nada. Right? Thank you very much.